Welcome to the next video in our lecture series dealing with geometry. Today we're going to talk about polygons, part 1. This is in section 10.4 in your textbook. What is a polygon? By definition, a polygon is a closed two-dimensional shape classified by the number of straight line sides. In other words, when we talk about these shapes, there will be no curved lines. No parabolas, no circles. A circle is not a polygon. They're classified in general by the number of sides it contains. Some have subcategories or subclassifications. For example, we've already talked about the subcategories of triangles. A triangle by definition is simply a polygon with 3 sides. However, we discussed that there were right triangles, acute triangles, obtuse triangles, scalene triangles, isosceles triangles, and equilateral triangles. Those will all be considered subclasses. It's a triangle, but we can be more specific and actually get more information based on that information. We'll also talk about the subcategories of a quadrilateral. Speaking of, so we have different types of quadrilaterals, and depending on the relationship between the sides, will give us a better picture. A quadrilateral, by definition, is simply a 4-sided polygon. In other words, a polygon that has 4 straight edges. However, depending on whether all 4 sides are the same measurement, or parallel, or whether we have 2 pairs that are equal, or whether we have 2 parallel sides that are not right angle, that do not meet at right angles, or only 1 pair of parallel sides, or a slanted, we like to say also slanted square. A parallelogram is simply a slanted rectangle. A rhombus is a slanted square. Please note that we want to be as specific as possible when it comes to classifying these. For example, every square is a rectangle, but not every rectangle is a square, by the definition. You should be aware of all 5 of these definitions when it comes to a quadrilateral. So if you're asked to classify a quadrilateral, you need to look at the information that's given to you to determine which of these subclassifications is required. So let's practice. Let's talk about identifying quadrilaterals. Let's go ahead and, oops, there we go. Go ahead and use blue. Let's identify these polygons. We want to determine that we're going to go by the number of sides. So here we have 1, 2. We have 1, 2, 3, 4, 5, 6, 7, 8 sides. Since we have 8-sided polygon, then this is called an octagon. Octagon. This is an octagon. Here, in the next figure, notice that we have 4 sides. We know it's a quadrilateral, but can we be more specific than that? We look at the sides and its relationship. We notice that these 2 sides, this opposite sides, are parallel, and then these 2 sides are also parallel. However, the corners do not form right angles. Does it look like all 4 sides are equivalent? So I know that in our videos in the past that we have to be careful about us making assumptions, but considering this is simply simple shapes, we're going to assume that all 4 sides are equivalent in this one, just like they're all 4 equivalent here. So this one would be a rhombus. Take a moment to figure out the other ones using our textbook if you are not sure of the name. Hopefully you pause the video and you're able to figure out the remaining 6. We have square, we have hexagon, we have a trapezoid, we have a rectangle, we have a parallelogram, and we have a pentagon. Some of the things that we are going to talk about in this polygon unit is going to be formulas. Specifically, we're going to talk about the angles of these polygons. We've already talked about the interior angles of a triangle. Remember that the sum of the three angles in a triangle equals 180 degrees. Now, if we have a different polygon, say a quadrilateral, does that relationship still hold? And the answer is kind of. We don't have exactly 180 degrees if we increase if we increase one more side, because now again we have one more angle. And unless those angles were to all shrink or get smaller, the sum would not be the same. In fact, the sum is going to increase. However, there is a relationship between the sum of the interior angles and the number of sides, and that can be found here. If we know n, the number of sides of the polygon, then we can figure out the sum of the interior angles. Remember that for a triangle, n is 3. So 3 minus 2 is 1 times 180 is 180 degrees. But if we were to increase it to 4, we'd have n minus 4, or n minus 2, which is 2, and then 2 times 180 degrees would be 360. What that means for us is that the sum of the interior angles of a quadrilateral, aka four-sided polygon, would be 360 degrees. We also can find the measure of an interior angle of a regular polygon. Now, a regular polygon is simply a polygon where all the sides are congruent and all the interior angles have the same measurement. This is why the formula is really nice, because if every single angle inside the polygon is the same measurement, then we can easily calculate it based on this. Note that the sum formula, the first one we talked about, this can be no matter how the polygon is. So even if it's an oddly shaped pentagon or an oddly shaped hexagon, we can still use this formula. However, these formula for the interior and exterior angles specifically require regular polygon. So make sure that if you're using the formula for an interior angle and an exterior angle that you already have a regular polygon. Otherwise, this formula will not work. Now let's practice. We're going to find the sum of the measures of the interior angles in these three different polygons. What we need to know is we need to know what is the value of n, aka the number of sides the polygon has. In the first one, we have a pentagon. By definition, the pentagon has 5 sides, so n equals 5. So we want to find the sum of the measurements, so s is equal to the quantity of 5 minus 2 times 180 degrees, which is 3 times 180 degrees. Using our calculator, we get 540 degrees. Now this is the sum of all angles inside the polygon. This does not mean that each angle is 540 degrees. It doesn't mean that we don't have anything else other than just the sum of it. In an octagon, we need to figure out what n is. Remember from that identifying exercise? This is 8. Think of oct, like October, even though I know that's like the 10th month. But it was supposed to be the 8th month before they added a couple other months. It's weird, I know. It used to make sense. But anyway, we have n as 8. So s is going to equal 8 minus 2 times 180 degrees, which gives me 6 times 180 degrees, which is equal to, which should be twice as much as the previous one. You might be thinking, wow, these are really big numbers. And that's okay. Remember, we're not measuring individual angles where we expect it to be no bigger than 180 degrees. We're measuring the sum. So if each angle was 180 degrees, and then you have 5 angles, well, that's 580 times 5. So these numbers are going to get bigger depending on how big you are. Now we have a dodecagon. This, shoot, it's either 10 or 12. I want to say 12. Well, we'll do both. And it's 12 or 10. Your book doesn't actually go this high, which is why I can't remember which one it is. But in either case, if it's 12, we do the same thing. We just replace that number into the formula, and we'll either have 1800 degrees, or if it's 10, then we'd have 8 times 180 degrees. $100. Cool. Yep. Next. All right. What if it's the interior angles? Remember, this one is the one that involves A. A equals n minus 2 times 180 degrees over n. Again, as long as I know what n is, we're going to get this right. All right. We're going to just do the first two because I don't want to go any farther, or I don't want to confuse anyone if this is a 10 or a 12. So we'll just do the first two. We know that here n is 5. So we're going to plug that into our formula. Anywhere there's an n, we're going to go ahead and put 5. Now we know from the previous problem that this was 540 degrees divided by 5. So we'll take 540 and we're going to divide that by 5 and we're going to get 108. But this tells me that if I have a regular pentagon, each interior angle is 108 degrees. That's all it tells me. This gives me a little more information. However, I don't know how long the sides are. I just know that there's 5 angles that are 108 degrees. With an octagon, we have x equals 8. So A equals 8 minus 2 times 180 degrees divided by 8. So then we had that 10,080 degrees divided by 8. So each angle here is 135 degrees. So if we have an octagon, then each interior angle is 135 degrees. Now let's work with the exterior angles. Remember, this one was B equals 360 degrees divided by n. As long as we know n, we can find the measure of the exterior angles. Again, n is 5 and n is 8. So B then, the measure of the exterior angle, is going to be 360 degrees divided by 5. 72 degrees. If we increase the size of the polygon in terms of its size, or sides, number of sides, we would get B equals 360 divided by 8. Would we expect that this number to be smaller or larger than this one? Hopefully, you said smaller. Remember that more angles is going inside of the polygon, which means the outside angles must be smaller. This kind of leads to circles, because if you were to increase the number of sides towards infinity, you're going to end up getting a smooth surface or a round surface, like as a circle. Okay. All right. So now it's your turn. I want you to pause the video to see if you can get the answers to these 3 questions. Right, hopefully you've paused the video so you gave yourself some time to answer these questions. Here's the results. The first one, you have 720 degrees. The second one, so this is 720 degrees, and then we have approximately 128.57 degrees. And then we have 90, oops, I forgot a little degree there. Degree. Then we have 90 degrees. So we'll talk more about this in class, and we'll do a little more practice with it. Until next time.